Okay, that's time, please. If you could, please just gather them all up and just kind of pass them all the way down here. Get them to this table over here, please. All right. Yeah, let's see here. Okay, thank you. Anybody else? Ma'am, how do you pronounce your name? Ashley. Is that the way it is on the roster or no? It is? Okay. Can you be my projector person? What I need you to do you see there's two red lights? The one to the right, I think it says VGA. Top row. Yeah, can you hit that, please? All right, let's talk about this. Can you all see that okay? All right, so here's the first problem. And the substitution, the correct substitution was u is equal to 1 over x. And that's because you could rewrite this integral. You could kind of peel that x squared on the bottom out, and you could even take that negative and bring that out. Negative 1 over x squared is exactly the derivative of 1 over x. And so if you see that, then you can see that this can turn into cosine u, and that is the derivative exactly, so it gets replaced by du. And then you're just doing the antiderivative of cosine u, which is just sine u plus c, then replace u with 1 over x. All right, so that was the first one. The second one, I saw a lot of people, not in this class, but in my other class, I saw a lot of people take the entire denominator as u. The problem with that is if you took the entire denominator, the derivative of 1 is 0, but the derivative of sine squared x, you have to do chain rule. So 2 has to come out, then sine to the first power, then derivative of sine, which is cosine, and you don't have that sitting here. You have a cosine, but you don't have another additional sine, if that makes sense. So this is, again, that trick of grabbing just enough, not too much. You just want to grab sine x. That's it. So if you rewrite sine squared x as sine x squared, then you can see derivative of sine is right up here, cosine x dx. I actually peeled the cosine x dx off to the side, then replace sine x with u, and replace cosine x dx with du. And that's one of the ones that you should recognize, 1 over 1 plus u squared. Antiderivative, that's arctan. So arctan u plus c, replace u with sine x. Good? No? All right, this one. This was one of those ones where you make a substitution even though it doesn't look like it's necessarily going to work. So you're going to take the radicand, x plus 4. The derivative of that is just dx. So you'll be able to replace this under here with u, but then you have to take care of that x. And so you go back up to this equation, you solve it for x, you get u minus 4. So we're going to replace the x with u minus 4. We're going to replace this x plus 4 with u, and it's a square root, which means 1/2. And then you can distribute. Oh yeah, the dx becomes du. You distribute through, and it's just exponent properties, and then you do power rule on each one of those. I messed up on my key, I accidentally put plus, but those are minuses. And then you mess with the numbers, you get your power rule to work out. And once you do that, you replace your u's with x plus 4. So that's what we're looking for there. Yes?
I wrote that where it was all over 15.
So like you got a common?
Yeah, I got a common denominator.
I just have to see to make sure it's right. Okay, and then the bonus was you had to recognize on the bonus that x to the 4th is actually x squared squared. And if you recognize that, then you can call u x squared then the derivative of that is 2x dx, which is exactly what I put up top. So this just becomes 1 over, u squared, and then du exactly. And again, that's arctan, so arctan x squared. So what did y'all think? Eh? Okay?
I think it was better than the first one.
So, I don't like giving quizzes every day. I mean, it's not, if I had my option, I wouldn't give a single quiz all semester. But I think this is a way of kind of, number one, keeping you on track, like as far as, look, I expect that you know how to do substitution to some degree by the next time we meet. And then it also gives you some idea of I guess, the types of problems that I might give you. And then also the reason I time you is because I need you to understand, that time is critical in this course, especially in terms of the exam. Because it's not just can you do it, but can you do it efficiently? That's part of this. I'm sure if I gave every one of y'all that quiz take home, right, and you had enough time, you could probably all do it, right? But part of this is how quickly can you recognize the pattern, do what you need to do, get it done, move on to the next problem. All right? So we're just practicing. Don't worry, I'll drop at least one quiz, maybe even two. It just depends on how many we take. All right? So, pardon?
So we want to take more.
I think you want to take more. I don't want to give more, like I said. It just eats up way too much time. We've eaten up a good 20 minutes of class, and we need that time. So, all right. Would you mind switching over back to the same one to HDMI? Thank you. So most importantly, I hope that you feel like that was fair. I just went and kind of looked at the homework problems and kind of just adapted a few of them, changed them a little bit. Now I have your quizzes from last time here, and I also have the bonus if you turned in bonus. So I'm just going to pass this packet around, and just please grab yours and just pass the packet to the next student, please. So we'll start here. All right, today we are going to continue with what we ended class with, and that was with me trying to convince you that we could use a certain formula to help us do some tougher integrals. And it was called integration by parts. I put it on the board over there, but that's not going to show up on camera. So I'm going to write it again here. And then I'll erase it, and then I'll just be pointing over there in a little while. Oops, I already messed that up. All right, the key to this formula is that it gives you an option to try and convert an integral that you cannot figure out into, well, there's some stuff in front, but it creates a new integral. And the hope is that this new integral is easier for you to do. And the way it's going to work for you is by recognizing what I said last class, the transferring of the derivative. So please pay attention to what happens to you in this formula. What you'll have here, is that blue? What you'll have here is some function here, all right? Whatever that is, separated from something else by multiplication. And you'll notice that in the new integral, that it's not u, but du, which means it's the derivative of whatever this was. So think about, like, if this was x, in the new integral, it'll be what? Dx, or 1, which means it's become a little easier to deal with, hasn't it? It's almost gone away, right? X is going to go to 1, or 1 dx. So we're able to transfer the derivative. Now, the give and the take here is that if you're going to use the formula, something is going to happen to the dv. So this piece right here, whatever it is, when you go to the new formula over here, it's not dv, it's the v, which would be the antiderivative, right, of that. So it's like we differentiate to get from here to here, and then the dv we integrate. So can you kind of follow what I mean by transferring the derivative? It goes from, they switch places. Yeah? Okay, so we're going to start off our first example. We're going to start off with a pretty straightforward one, and I'm going to do what I did last time. I'm going to still call on people, all right? and see what you're thinking, all right? So here's our first example. Let's go with x sine x dx. And let's see who the lucky one is. Now, I will take volunteers, but you can't volunteer if you already did it last time. So I have a list here of who already has participated. Who's going? Okay, what's your last name again?
Hernandez.
All right, let me mark you. Tristan. Okay, so Tristan. You need to try and come up with what you are going to call U and what you are going to call DV from that.
So call it UX.
UX
XU.
and DV you want to be what?
Sine X.
Sine X, and always grab the DX with it, all right? The DX part will always go with the DV. Now, I like to do this in like a systematic way. I like to use a table. So every time I do an integration by parts problem, I'm going to draw a table. And I'm always going to start with the top left corner being U and the bottom right corner being DV. That's the way I always start my integration by parts. By the way, before we actually do this, we didn't have another way of doing this, right? I mean, there's, like if it was just sine x, you'd be in business, right? If it was just x, you'd be in business, but you can't do them individually. So we don't have any technique right now that will handle this, but recognizing that it's a product of something and something, integration by parts should come to mind.
You said DX always goes with DV, right?
DX will always go with DV. So the choice has been made to let U be x, and that means everything else has to be dv, sine x dx. Now, in the new integral, we're going to have v and du, right? V and du. So let's go complete this table. And the way I do this table is down is differentiation and up is integration. All right, so if I want to go from u down to its derivative, I would write du, and Tristan, what is that going to be? Am I saying that right, Tristan, right?
Yeah.
Okay. What's the derivative of x? 1 dx. So it's your choice. You can write 1 dx, or you can write just dx, but don't just write 1, okay? Dx, like that. And then, Tristan, we have to go up, all right? So this means it's almost like you're going to do this, integral on this, and go up to this. And that should generate v, shouldn't it? Okay, so what's that going to be, Tristan? What's the antiderivative of sine? Negative cosine x, right? Everyone got that? Negative cosine x. Good. Now, the big question is this going to work? Okay, is this going to work? Because integration by parts does not always work. The key is whether or not this new integral is something you can handle. So what I like to do at this point is look at this. This is going to be v times du, which if you look in your table is the diagonal, isn't it? It's going to be this one times this one. So just in your mind, try and visualize that new integral. So I'm like visualizing this. Okay, I've got my eyes closed. I'm visualizing this new integral. It's got negative cosine x dx, right? Oh, wow. I should open my eyes. Cosine x, right? That's what that would be. It would be this one times this one, but in an integral. And when I think about that, I know I can handle that, right? Yes? That x is vanished, which is what I wanted. So I give the thumbs up, and that means let's just keep going now. Understand what I mean by this? Yes? Come on, it's 3 o'clock. I'm sick, and I'm more excited than you all are right now. All right, so here we go. Tristan, let's just apply the formula now. Okay? Tristan, this is equal to what? So just read me out the formula over there. This integral. Yep, go ahead. U times v, which is this times this, right? No integral, just this times this. So wouldn't that be, if I try and rearrange things like negative x cosine x? Agreed, everyone? And then continuing the formula, minus, right, minus integral, and this was that one that I visualized, but it's just the diagonal. Negative cosine x, and then what? Dx. Now, can you kind of see why I said don't put 1 here? Because if you put 1 here, you're not going to have a dx in that integral, and it's not going to look right. It's not going to be proper notation. Now, Tristan, can I do anything before I actually integrate that? Is there something that you see that I see there? Like, this is really like a -1?
Yeah.
Could you pull that out? Sure, and that should make it a plus integral, shouldn't it? I like to, once I have actually applied the formula, integration by parts formula, I like to actually pull any constants out first. And now, this just breaks down to the antiderivative cosine x, which is, careful, antiderivative cosine, sine x, so plus sine x, and then plus c. And we have the plus c because we actually took the antiderivative, so we're always going to have a constant there. Everyone see that? Good. Now, there was a little mnemonic that we were using to remember this formula. Do you all remember what the little mnemonic was? Ultraviolet minus voodoo. Do you all remember me saying that? No? I didn't put that on the board last time? This formula, you can use this little ultraviolet minus voodoo. V-O-O-D-O-O. It's just a way of remembering the formula. It's ultraviolet minus, now you have to remember there's an integral, okay? Ultraviolet minus voodoo, all right? V-D-U, voodoo. And why is it that? I don't know. Someone told me that a long time ago, and it just sticks, okay? Ultraviolet minus voodoo is one of those things that just sticks. Now, this formula is on your formula sheet. I believe it's formula number 1. Somebody check.
For a second, I thought you meant that.
What is? Oh, the mnemonic's on there? No, it's not. But it is, right? That the first formula on the table of integrals? Okay. All right. Good. We're done, right? We're done? This is it? We're finished? Now, that means that if we take the derivative of this, right? If we differentiate this, what should we get back if we differentiate that? We should get back x sine x. Should we check it? Sure, we'll check it. All right, so let me just do a quick check of this. If I do a check, if I differentiate this, that's a product right there, isn't it? So I've got to go derivative of this one, which is -1 times this one, plus the derivative of this one, negative sine x, times the first one, negative x, and I'm done with the product rule, plus derivative of sine x, cosine x, derivative constant is 0, and you'll notice that I put these two together, right? I have two negatives, that's going to be a positive. That's going to be x sine x if I rearrange it. And then this is negative cosine x, and this is positive cosine x. And so these two cancel out, and you're left with x sine x. So it works, right? Pretty nice? Okay. All right, let's get another victim here. Is anyone going to volunteer for the next one? We go? Okay. Last name? That's what I thought. Okay, Rufino. I am kind of following the notes. Here are the notes for today. There's really not much. It's just like 5 examples or 6 examples that I'm going to do. I'm going to try and do all of them. Well, actually, there's no way I'm going to finish them all. I'm probably going to get through 4 of them. But I'm also going to tweak them a little bit. I'm going to do kind of my own variations of them. So let's do this one. Let's do x cosine 4x dx. Oh, you know what? Yeah, I'll do it on this one. Never mind. Louis, you're up, right? All right, what do you got?
Use x and dd is constant for it.
Use x. What do y'all think of that? Use x? Yeah, because when it goes to the new integral, what's it going to be? Dx. Now, what I want to do is, just for the sake of illustrating, let's act like we totally just jacked this one up, okay? So don't write this down, but let's just pay attention to what would happen if we accidentally pick it wrong. All right, so what if I did this? What if I wanted to let the cosine 4x be my u, and the dv would be everything else that's there? So I'd have x dx here, right? Well, I can still differentiate this. Derivative of that is negative sine 4x, but then I'd have